Welcome back for more physiology. This particular talk, we're going to deal with capillaries, that last blood vessel that we've kind of been ignoring for a long time. So, in particular, what we want to deal with is how do they control themselves? How do we make blood move? Easiest way to explain it is blood goes from high pressure to low pressure. That's how things tend to go. So pressure, we know, can force blood to move. Blood is primarily water, so pressure must be a way that we can make water move. Seems easy enough. If I look at the job of circulation, which is to replenish the watery environment, so take away what's bad, put in what's good, and keep this thing going. Don't let it get stagnant. Keep it moving, keep it moving, keep it moving. The place where all of that occurs is at the capillary. So capillaries are made out of simple squamous epithelium. They're one cell thick, and it's going to be the easiest place in order to have that exchange. And what we notice when we look at this is there's two things that basically can happen. We can have stuff flow out overall, and we can have stuff flow back in overall, meaning going from capillary to the tissues or the interstitium, and then going from tissues or interstitium back into the capillaries. Those are the two major options. I suppose you could say that overall there's nothing happening, but for the most part you can get one of those two things. So the pressures that are involved come from two different sources. One of those sources would be a physical push, meaning you have pressure inside of the blood vessel and it's physically pushing water out. But tissues also have pressure, so you could physically push water into the capillary or into the blood vessel. I say blood vessel, I should say capillary. But there's another thing that's at work here too, and that is osmosis. Even though pressure is dealing with osmosis, we can talk about osmotic pressure in terms of solutes, meaning I have stuff, namely proteins, dissolved inside of a blood vessel, the capillary, and that is going to draw water into it because proteins draw water towards themselves. So having proteins dissolved in the capillary will draw water into the capillary, but having proteins dissolved in the tissues in the interstitium will draw water out of the capillary and into that space. So what we can end up doing with all of these pressures is we can actually kind of start to put them all together. So here's a basic problem where I have 4 different pressures listed. 2 of them are the push pressures, what we would call hydrostatic pressures, and 2 of them are the pulling pressures, what we would call the oncotic pressures, that are colloid oncotic. Colloid is a nice word that means protein, oncotic meaning due to osmosis. So if I look at the pressures that would be forcing water or blood or liquid, whatever you want to say, from capillary into interstitium, the blood pressure would push stuff out, so that would be the blood hydrostatic pressure. And the tissues have a oncotic pressure that's going to suck the liquid out of the capillary and into the tissues. So that'd be the tissue oncotic pressure, or TCOP. So the top and the bottom numbers deal with pushing liquid out. We call that filtration. So how do you figure it out? It's 30 plus 8, 38 millimeters of mercury. Got it. If I want to make liquid go back into the capillary, what could cause that? Well, I have a blood pressure or a water pressure outside in the tissues that's going to shove liquid into the capillary. That's interstitial hydrostatic pressure. But I also have proteins dissolved in the capillary, and that's going to pull the water in, or blood colloid oncotic pressure, or BCOP, which are those middle two. So what do we have? 38 and 8 are 38 millimeters of mercury saying let's go out. 28 and 3, 31 millimeters of mercury, is going to say let's go back in. Let's take it back or reabsorb it. The question then becomes, what's a greater number, 38 or 31? Hopefully you know 38 is the bigger number, which means filtration or net filtration is occurring. Seems easy enough, which is what I just said. See if you can do this one on your own without me. Did you get it? Easy enough. What we'll notice is for every 100 milliliters that gets filtered, about 99 gets reclaimed or reabsorbed. So we need that 1%, because it turns out that 1% is kind of a big deal. So we have a tissue or a vessel called a lymph vessel, and among its jobs is it can reclaim that 1%. And they're sometimes called blind capillaries, even though they're technically not capillaries. They are incredibly low pressure, so the result is they need to have valves, and they end up pouring into different parts of the body. Your right arm has its own version, and everywhere else in your body has its own low duct that it can go to. We tend to have issues with lymph vessels when it comes to cancer and cancer metastasis, and sometimes lymph vessels get cut out because we need to worry about it. They have little bumps along the way on these lymph vessels, and we call them lymph nodes. They swell up when you're sick. It's a quick and easy way to diagnose, are you really sick or are you faking it? So we can finally get to the point of this. How do these things open and close? This one is a bit of a trick. I'm going to have to stare at the screen in order to point it out. And so hopefully you can follow the pointer. So what we have are, at these capillaries, we'll have these things called precapillary sphincters. As all a sphincter turns out to be is a ring of smooth muscle that is a tight fist or a looser fist. In both cases, I have a fist, but the difference is tight fist, not as tight fist. Tight or not as tight fist, stuff could probably flow through. Really tight fist, yeah, not so great. The catch is, if they're loosely closed, blood flows through the capillaries. You get capillary exchange. Nutrients pour out. So blood flows out of these out of the capillaries. We have net filtration. What that's going to result in is we have nutrients. Those nutrients get metabolized by the smooth muscle cells. When they have energy, the result is the sphincter is going to close, because you can now have muscular contraction. When it closes, the result is that everyone's walking into the room and I need to finish this video. We stop blood flow. Well, if there's no blood flow, we don't have any nutrients flowing in, which means we can't maintain the contraction, and it opens back up. Blood flows out again. Blood flows out, we get nutrients. The result is capillary, or the sphincters close, no blood flow. But now there's no energy, so they open back up. Now we get blood flow, nutrient exchange, muscle contracts, and that cycle just keeps on going. How do these things know when to open and close? They just do it. Can this ever go wrong? Sure, if you have too much capillary exchange, so we have too much filtration, you get this phenomenon here, which is called an edema. There's various versions of edema, but this one here is called pitting edema, meaning you can push on it and it leaves a dent. Hence, in the left picture, being pushed on the swelling, and on the right, you see the dent remaining. Can this ever go wrong? Absolutely. So with edema, but also this turns out to be a phenomenon that shows up with inflammation.